We are on page 42 and we are going to be talking about the efficiency of a machine. A machine is used to change energy from one form to another. Remember what we said, energy cannot be created and it cannot be destroyed. It can only change from one form into another. The total amount of energy that is given to a machine is always equal to the total amount of energy that the machine gives out by the principle of conservation of energy. The blank over here is an error. You can leave that out, leave it empty, okay? Because it is the principle of conservation of energy. Usually, the wasted energy comes in the form of heat energy. Now, a machine is never 100% efficient. So if we take an example with cars, most cars that use petrol, their efficiency can be as high as 37%, but most commonly 20% is a more common number. And if we take cars that use diesel as a fuel, that is a bit higher, okay? So the maximum efficiency diesel cars can get is up to 41%, but a more common value would be that of 30%. Okay, so we're saying that everyday cars that we use only have an efficiency of between 20 to, let's say, 35% efficiency. So only 35% of the chemical energy we are supplying, we are getting kinetic energy from. Because from a car, that is what we want. We want the kinetic energy of the car. We don't want the heat that it generates or the sound that it generates. The efficiency of a machine is a ratio of the useful energy obtained from a machine to the amount of the energy given into the machine. It can be expressed as a percentage using this equation. So efficiency is the useful energy output divided by the total energy input multiplied by 100. Now let me repeat. Energy cannot be created or destroyed, which means that if I were to supply a car with 1000 joules of chemical energy in the form of fuel, all of that 1000 joules is going to be changed. None of it is going to be destroyed. However, not all of those 1000 joules are going to become useful for me. Again, if we take the example of a car, as you know, as a car works, it heats up. I don't need that heat coming from the car's engine. That is useless for me. Also, the sound a car generates, that energy, that is not useful. It doesn't help us in getting from point A to point B. The only form of energy that we want out of a car is the kinetic energy, the movement of the car. So efficiency is the useful energy output divided by the total energy input multiplied by 100. Let's work out a couple of examples to see how this equation can be used. Worked examples. Number 1. A bulb uses 20 joules of electrical energy. 5 joules are useful light energy, and the other 15 joules are energy heating up the bulb and the room. Calculate the efficiency of the bulb. So as we can see, this bulb has an input of 20 joules, of which only 5 are useful. Obviously in this question here, you've been helped a bit because the examiner here is identifying what is useful and what is not. The other 15 joules are energy heating up the bulb and the room. When we talk about light bulbs, we never really need the heat coming out of a bulb, unless, as you had in a previous question in one of the homeworks, you are a farmer that is raising chickens. Because sometimes farmers do use light bulbs that heat up a lot when they have electricity passing through them to keep baby chicks warm and help them as they grow, a sort of incubator. But the normal light bulbs you use at home, the only thing we want out of the light bulbs is the light. We never need the heat. And if you're going to heat up a room, like this question is suggesting, well, you're not going to use light bulbs, you're going to use a heater or an air conditioner, an appliance that is specifically designed to heat up a room. So let's calculate the efficiency of the bulb. As usual, we always have to start off from the equation. This equation that we've been given over here, that you have to No. Efficiency equals useful energy output divided by total energy input multiplied by 100%. In this case, the useful energy output we said is 5 and the total energy input is 20. So let's plug those values in. 5 divided by 20 multiplied by 100 will give us 25%. So this light bulb is 25% efficient because only 25% of all of the energy going into it is coming out as energy that we need. The rest of the 75% is being sort of wasted to forms of energy that we have no use for. Let's move on to question 2 on page 43. In a car, for every 200 joules of chemical energy, 20 joules is used to drive the car, and the rest are wasted as heat. Question A. Calculate the efficiency of the car. So let's see. The chemical energy here is going to be the total energy input, whereas the 20 joules, that will be the useful energy output, because even the question itself is saying the rest is wasted as heat. We don't need the heat from a car. Okay, what we want is the car to drive, to move. So let's calculate the efficiency of the car. Starting off from the equation, so efficiency is the useful energy output divided by the total energy input multiplied by 100. 20 joules, which is used to drive the car. 200 is the total energy input and multiplied by 100. So 20 divided by 200 multiplied by 100 will give us 10% efficiency. Question B. What amount of energy is wasted? What we have to figure out is, if out of 200 joules only 20 are useful, how much is being wasted? And this is simple because all we have to do is minus the total energy input by the useful energy output, which is 20. So 200 minus 20. In this case, the car is wasting 180 joules. Question C. In what type of energy is the wasted energy converted? Now, since this is a car, even in the question we already have indicated. He already suggested that the rest is wasted as heat. So there will definitely be thermal or heat energy. But from our experience with normal cars, there will also be some sound. So sound energy as well. Question 3. An athlete in a race exerts a force of 80 newtons to run a distance of 100 meters. He uses up 40,000 joules of the consumed food energy. Calculate his efficiency. Now this question has two parts to it, because even though we are being asked to calculate his efficiency, and we do have a total energy input of 40,000 joules, but we do not have the output. What we do have, however, is a force and a distance. And we've learned that when I have a force and a distance, I can multiply them together to figure out the work done, which we said can sometimes be referred to as the amount of energy transferred. So what we have to do here is first multiply the 80 by 100 to get the work done that the athlete is doing. And then we have to figure out the efficiency by comparing it to the 40,000. So the first step would be writing the equation of the work done. Let me remind you, is W equals Fs. Plugging in the values, we will get 80 multiplied by 100. That will give us 8,000 joules. Now that we found the useful energy output, we can compare it to the 40,000 to figure out the efficiency. Again, we have to write the equation for efficiency, which is efficiency equals useful energy output divided by the total energy input multiplied by 100%. Plugging in the values, we will get 8,000 divided by 40,000 multiplied by 100, which will give us an efficiency of 20%. Here we are seeing how one equation can be used in relation to another, how equations can be brought together so that they make sense and they can make our calculations a bit more difficult. if we don't know how to use the equations, which is why we have to practice and remember what the equations mean and how they can be used. Question 4. A petrol engine uses 80,000 joules of chemical energy, of which 20,000 joules are useful energy. On the other hand, a diesel engine gets 20,000 joules as chemical energy, of which 7,000 are useful energy. Question A. What is the efficiency of the two engines? Now, since we have to compare the two engines together, we have to split the working zone into two. We'll have petrol on one side and diesel on the other. So let's start off with the petrol. Starting off from the equation, we have efficiency is equal to the useful energy output divided by the total energy input. I've written it a bit abbreviated so that it takes up less space. Plugging in the values will give us 20,000 divided by 80,000 multiplied by 100%, which will give us 25%. Doing the same thing for diesel now, so efficiency is equal to the useful energy output divided by the total energy input multiplied by 100. When we put in the values, we'll get 7,000 divided by 20,000 multiplied by 100, which will give us 35% efficiency. Question 4b. Calculate the percentage of energy wasted in the two engines. Now once again, let's take petrol. If 25% is the useful energy, then 100 minus 25 will give us 75% of the energy is wasted. In the case of diesel, 100 minus 35 will give us 65% of energy that is wasted. Question C. Which is the most efficient engine? If we simply compare the answers we got in part A, namely 25% and 35%, it is very clear that the most efficient engine is the diesel engine.